Good evening, everyone, and welcome to this month's Atom Society live streaming event, and what I hope may well be our last streamed event. Fingers crossed. We've got another really interesting talk lined up for you this evening, and I'm really excited about it. So just let me run through a few admin things first. As I said, we are hoping that this will be our final live streamed event. I know that you're, I'm sure, all very excited about the talk we have coming in July from Frank Close, and that is scheduled to be our first in-person event, and our return to seeing all your lovely faces instead of just seeing my face every month. That being said, the Society had not originally planned to have a talk in June because of the festival, but with the festival being a bit smaller this year than it usually is, we're hoping we might be able to squeeze one final live streamed event in. We're busy trying to find a speaker at the moment. It's quite last minute. We normally book about a year in advance. So if any of you out there in internet land have got any suggestions for someone who you've seen speak and think would be really great for our society, please get in touch and let us know, and we'll try and see if they're free. Additionally, obviously the festival is still going ahead in a much reduced format to usual. So it will be the 11th to 13th of June, and they're really keen to get people involved with their SciCash event. So head on over to the Atom Festival website, take a look at that and see if you want to get involved with that. And similarly, if you would like to volunteer, please get in touch with myself or Susan to register your interest for any volunteering that may be required, and Susan will be able to let you know if you'll be needed. Okay, so before we move on to the main event, it is, of course, time for this month's science snippets. So if you have any snippets lined up for us, please do let us know. I've got one myself, but I know that James has got a couple, so I'll bring him in first. James, what have you got for us?
Yes, hello, good evening, everybody. I've got a couple of snippets for you today. One is from Japan and one is from Sweden. First of all, the Japanese one. It's sort of associated with science, but not quite involving a scientist. Anyway, there's a philosopher and writer in Japan called Yokio Hiroshi, who has an office overlooking a village square or a town square in Japan somewhere. I'm not quite sure where it is. And overlooking the square, in the square there are a number of statues, mainly bronze statues. And he noticed that all the statues bar one were covered with pigeon droppings. He wondered why the one that wasn't covered. So he had a friend who was a physicist, or chemist rather, and they managed to get a sample of the material that the statue was made from and tested it. And they found that as well as the normal copper and tin bronze consists of, it also had about a 5% content of arsenic. I thought, oh, well, this is interesting. And they knew a sculptor who'd been commissioned to make another new statue for the same square. And they got in touch with him and said, look, when you make this thing, will you put some arsenic into the mix? And let's boost it up a little bit. So they put 10% of arsenic into the mix to make this new bronze statue. And they did, and the statue was erected, and not a single pigeon sat on it. So it obviously worked. So well did it work that the local authority decided that they would now commission all future sculptures in the town made of bronze to have this content of arsenic. So my advice is, if you go to Japan and see some statues, don't touch them. Or if you do, watch them afterwards.
No licking of statues.
Well, my second one is more zoological, and this is to do with Lund University, some researchers in Lund University, and this one appealed to me. They were researching into the communications between certain animals, and in this case it was crocodiles. I wanted to see whether they had a feeling that the depth of the sound of a male crocodile in wooing mood, so we say, may have an effect upon the females. And so they got hold of a male, put him in a large tank with a recording device, and they first of all filled the tank with air, ordinary air, and they recorded his voice. Then they put in a 10% mixture of helium into the tank. You know, if you breathe in helium, your voice gets a bit squeaky. You probably tried it sometime or another. And so it was with the crocodile. So this big bull crocodile, now with the helium mixed in his lungs, made a slightly squeakier croaking sound, roar, and they recorded that as well. Then they let him go, I suppose, and they played recordings of both the normal voice and the squeaky voice to a bunch of female crocodiles in a zoo, expecting, of course, that the females would prefer the deep, throaty roar of the big male. They got exactly the opposite result. They preferred the squeaky voice. So if any of you men out there are thinking about amorous and you've got a squeaky voice, don't worry, you'll be fine. Okay, that's it. So back to you.
Thank you very much, James. That was great. We haven't got any comments.
Goodbye.
Bye. We haven't got any commentary on the chat just yet. If you do have any and you don't make it through, I'll try and come back to you later today. I do have one myself. Obviously, the events of the past year have highlighted a particular hospital procedure to a lot of us that we maybe hadn't thought about before, and that would be ventilation. So a process to help someone breathe when they're having lung difficulties. But the process of ventilation is quite violent, actually, and it can be very damaging to what is otherwise very sensitive lung tissue. Now, researchers in Tokyo think that they may have found an alternative way to get oxygen into our system. They have discovered something in pigs that they think may also work in humans, and that is they are able to breathe through their rectum. So with the aid of an oxygen-rich liquid, they submerge the back end of these pigs in this liquid, and then they decreased the oxygen available to them via their nasal passages in their lungs, and they found that the pigs were able to get the oxygen they needed from this liquid through an alternative orifice. It's very early days as to whether this would be applicable for humans, but yeah, an interesting insight. Oh, I'm getting something through. Peter, do you have a snippet? Do you have one you wanted to share with us? Wave if you have one. Okay, so Peter also has a snippet. Just bear with me. There we go. Hello.
Okay, let me see where I can do this. Right. I hope people can see that.
Oh, you're not sharing your screen, Peter.
Oh, okay. I thought I was. Right.
Just while Peter locates his screen, I've had something come through from Bob, who says that anyone who is on Twitter may like to follow Element Cup at Element Cup, where you can champion your favourite element in a silly but educational lockout competition. That sounds quite fun. Okay, Peter, I have your screen now. There we go.
Okay, yep. So this is slightly gruesome, but I did notice this short article from a couple of researchers in Ecuador, also zoological. They were surveying these sections of road alongside a national park, couple of national parks. And although that's not a very random way of sampling, they identified all the roadkill that they found. About a third of the specimens were actually opossums. I don't know if you know, but in New Zealand, opossums are an invasive species which are widely disliked because of their tendency to rob birds' eggs and everything else. Indeed, there are chocolate sweets in New Zealand called bush possums, which are shaped like a possum which has met its end under a car. They also found these little-known Sicilians, which are they're actually amphibians, but they don't look like other types of amphibian because they don't have any legs and actually it's quite difficult to tell which way they're moving because they look like shiny earthworms. They also identified or made a discovery of this snake that was new to science beside the road. One unfortunate demise was a very small but rare cat from that part of the Ecuadorian jungle. And so they thought about some ways of trying to reduce the effect of the road on the local fauna, but unfortunately the places where the roadkills were most common was indeed the bridges over rivers. So it seemed likely that the animals are using those bridges to get across rivers they wouldn't otherwise be able to cross. So the research continues to find out other ways in which they could mitigate the effect of rushing cars. I'll stop sharing and hand over to someone else.
Thank you very much, Peter. I know I quite like the little subways that you can get under roads for badgers and hedgehogs and things. They tend to work quite well, but I'm sure the researchers are on it. Thank you very much. Just following up from Bob's recommendation for @ElementCup, he says that it's round 3 today. It's Xenon versus Titanium, and Xenon needs some love. So you guys need to go over and vote for Xenon. Okay. So without further ado, we will move on to the main event. So yes, this evening we have a really, really interesting talk lined up from Professor Nick Hawes. Professor Nick Hawes is coming from us as an associate professor with the Oxford Robotics Institute, as well as a tutorial fellow at Pembroke College. He completed his PhD in artificial intelligence at the University of Birmingham before going on to have postdoc positions both at the MIT's Media Lab Europe and then at the School of Computer Science at Birmingham. And he has led his own team since 2009, researching artificial intelligence as applied to robotics, before heading on over to Oxford in 2017. So we're really excited to hear his talk this evening on an uncertain mission, decision-making for robots. And I will bring him into the stream now. There we go. And thank you very much, Nick.
Hello. Cool. Awesome. Can you hear me? Is that working?
Yes, it is working.
Super exciting. Cool. Thank you for the introduction, Danielle. And it was awesome to hear all of those science snippets. So yeah, my name is Nick. I'm an associate prof in the Oxford Robotics Institute, where I lead a group that does research on decision making for robots. I'll say a little bit more about that for when I get to it. I should also warn you that I'm using you all as a bit of a sort of a test run. So this is the first time I've given this talk to anyone really. So it might be a bit rough around the edges, but I thought you seemed like a friendly bunch to sort of try something slightly new with. So yeah, I'll be interesting to hear your feedback towards the end, and I'm happy to take questions kind of as and when you've got them. So I work in a lead a group that works on what we call sequential decision making, and the way to think about that is we want to control our autonomous robots to solve problems and complete tasks for us humans. And to do that, a robot typically needs a sequence of actions it can perform in order to achieve a goal. So we give a robot a goal, it comes up with a sequence of actions in order to move it, to change the world, to navigate around, to interact with things in order to achieve that goal. And that's a field we call typically in the AI community sequential decision making. And so my group researches a variety of algorithms, methods for sequential decision making for robots. So you can do sequential decision making for kind of voice assistants. You can do sequential decision making for other kinds of computer programs, but I'm particularly interested in doing this for robots. And I'll explain why in a little bit. And on here you can see a couple of videos of robots that we've worked with over the years, and they'll reoccur. And of course, up in the top corner is a picture of my fantastic group and all the lovely individuals in that. So I want to start by, I guess, trying to frame the talk around what is interesting and what is challenging in robotics. So if you think, often, certainly 10 years ago, if someone said kind of robots operating for businesses or companies using robots, I think everyone's mind would have jumped to manufacturing, where we had a huge robotics revolution from sort of the 70s, 80s onwards. And these robots are incredibly impressive pieces of engineering, but in terms of artificial intelligence, in terms of autonomy, they're very limited, very restricted. So robots in a manufacturing setting are simply machines that repeat a fixed script with very, very high precision, potentially very, very high speeds. And the reason they can just repeat this fixed script, this fixed sequence of actions, is because all the dynamics, all the things that can change the world are kept out of these settings. So in this, we often think of humans being kept out of these factories to protect them from being squished by the big machines. In reality, the reason humans are kept away from production lines is because they interfere with the processes and stop the robot's world being entirely predictable. And that's what we typically need to automate something. We want this entire predictability, and then we can automate a task such as manufacturing a car using industrial robots. So this is kind of maybe the history of robotics, or part of history of robotics. I think what's interesting now is to think about where we want to go with autonomous robots and autonomous systems in the kind of near term and in the future. So whereas 10 years ago I might have said robots and people have thought manufacturing, now we have autonomous robots in a wide range of shapes and sizes and applications. So from autonomous cars, autonomous mining vehicles, robots in supermarkets that you can see in the bottom left here with a robot doing stock take, robots working in warehouses, in shoe stores, and all these robots are autonomous, and they're autonomous. And what we mean by autonomous is that they can control their own behavior in order to achieve a task. So autonomy generally means some ability to control your own destiny, and for a robot that destiny is very limited. But the thing that's interesting here is the contrast to the factory setting. So in the factory setting, the world is entirely predictable, entirely fixed. In all the examples I'm showing you here, in fact, I might just jump back to the beginning of the slide and run it again. All the examples I'm showing here, the world is dynamic. There's variation. That variation may come from pedestrians, from people in a supermarket, from variations in the ground, from the way that boxes have been stacked on shelves. All of these are sources of variation that the robot does not know about in advance and can only know about by perceiving the environment with a collection of sensors. So this is where things become interesting for autonomous systems. They have to perceive their world using cameras and laser scanners and radar and sonar and all things like this. And they have to make decisions on how to act, how to move, how to interact with the world based on the results of those sensing processes. So autonomy is interesting and is necessary to deal with the variation in the real world. So what does that mean? Well, an autonomous robot has limited sensors. It's only got a range of a couple of meters to tens of meters for its sensors, and it can't fully perceive the world at any time, any instant. And what that means is we have to write computer software and algorithms that sit inside the robot that models the way the robot interacts with the world. And the robot uses that model to predict the way the world will change in the future and just predict the dynamics of the world. So an autonomous robot, all autonomous robots have some kind of model. And by model, I mean a kind of computational artifact, a bit of software that sits inside the robot. And the robot uses that to predict the way the world will change when it interacts with it. Now, that model, for various reasons, is limited. It's restricted. It's not of the same resolution of the world. And it can't fully predict the whole world because the world is stochastic, dynamic, moves in 3 dimensions and is continuous and all these kind of things. A robot can't model that exactly in its head, effectively in its software. So that means that model is limited. It can't accurately predict the way the whole world changes. And what that means is when we think about how a robot should change its own behavior, should plan sequences of actions in order to change the way the world is, well, that behavior has to reflect the uncertainty that the robot has. Okay, and that's where this talk is motivated from. A robot is inherently limited in its ability to perceive and predict its world. And that limitation means that the future of the world, when the robot acts in it, has some uncertainty. And what I want to talk about today is the methods we use to actually deal with that uncertainty and plan robot behaviors to reflect that uncertainty. And I'm going to talk about this from a perspective of kind of long sequences of robot actions. Other people in robotics work on kind of control, so how you would literally move the arm of a robot or steer a car for a meter. And that's one sense of action that requires you to manage uncertainty. But I'm interested in like long sequences of actions that might take hours or days to complete, where we have sort of uncertainty at both that kind of low level dynamic sense, but also a higher level sense as well. So I'm going to talk about the methods we use in AI and robotics to plan robot behavior such that it can manage uncertainty. Okay, so how do we do that? Well, there's a kind of process that's very common to actually a huge amount of statistical modeling, maths, AI, robotics, and that starts with us trying to quantify the uncertainty. So we want to be able to understand where the uncertainty is in an AI process, or a robotic process, and we need to measure that and model it mathematically. So we're going to use probability to do that, and a huge amount of robotics and AI is founded on probability theory. And we're going to factor that uncertainty into a model of our system. So in particular, we're going to model the actions a robot can perform and the states of the world. So how the world appears after an action has been applied. Then we're going to write down what we call a formal specification, a specification of what the robot's trying to achieve. So if the robot is trying to move from A to B, a formal specification might be the robot is at location B, or the robot is at location B at time at 3 o'clock, for example. So we'll write down some kind of specification of the goal the robot is trying to achieve. Sorry, I'm just going to unlock my timer so I can see how long I've got. There we go. And we're going to take that collection of a model, a formal specification, and we're going to solve it for what we call a policy. So a policy is simply kind of a set of instructions that the robot can follow when acting in the world. You can think of it as a plan the robot follows step by step, or even something like a lookup table where the robot has a list of the ways the world can behave. And for a given way the world behaves, it can look up a particular action to perform. And hopefully some of that will become a bit clearer as I go through some examples. Okay, so I'm going to start. I'm actually going to spend probably the majority of this talk trying to motivate the problem and give you an example of the kind of way we think about it. And after I've done that for a bit, I'll give you 2 examples of robot systems that we've worked on that use this methodology to achieve slightly different aims. But from if you squint a bit, they look the same. But I'm going to start by just kind of motivating all of this with an example that actually I showed in a video earlier. So this isn't work we've done with these particular robots, but we have thought about this problem from a planning perspective, which is moving ore around in a mining setting. So one of the big consumers of autonomy, of autonomous vehicles, is the mining industry, because it's incredibly hazardous, dangerous, and they've also got a lot of money, so they can afford to buy autonomous haulers, such as the ones we see here. And I'm going to give you an example from a paper that we found quite compelling, which is the problem of moving these trucks around and trying to optimize the amount of kind of the ore that you can move with a single truck. And the problem starts with what we're going to call the primary loader. So the primary loader puts the first load on one of these trucks. And for this task, I'll talk about it a little bit in reason why in a minute. We're going to assume that this actually works at a fixed frequency. And that's the way it works in a lot of these situations, that this is actually a device that just sort of spews out gravel or spews out ore into whatever truck is there. And we're going to actually model the world and have some time. So every time the truck gets loaded, that's going to take 1 unit of time. And that's a fairly standard way to think about these problems. We might divide the world up into slices of time, and everything that happens might take 1 unit or 10 units of time. So our robot gets loaded with the primary load, that takes 1 unit of time. And there's somewhere else on the map where it can get a secondary load. So we can get a bit of extra ore. And again, that's takes some time. And maybe this is a manual process. So, if the robot goes there, it can get a secondary load, but it doesn't have to go there. And then we're going to have a location where the robot can unload. So it's collected its loads at various locations. It goes somewhere, it unloads, and then we're going to represent or model these locations in our map. So we're just going to label them with circles, and these represent places the robot can move. And because we're a business in this example, we're going to get some money for every load we unload. We get some reward, is what we'd call it in an AI planning process. We can think of this as linked to utility, if you think about rational decision making. But we'll refer to this as a reward. So our primary load gives us a reward of 10 points, and our secondary load gives us a reward of 6 points. It's not as valuable to us as the primary load. And we have some kind of map of the world. So this map represents places the robot can drive, and the connections between these places represent routes the robot can safely navigate. So I showed you some examples on when the videos are running of robots moving around in the real world, and this just kind of demonstrates that this is a thing they can do. I'm not going to talk too much about that. That's not an area we actually work on, but you just have to trust me that robots can safely move in the world. And just like loading and unloading, well, navigation takes time. So in this case, we're going to make life easy and say everything sort of takes 1 unit. But now we're going to introduce the planning problem, the decision-making problem. So the robot has a map that allows it to navigate back to the unloading spot, and it can make a choice. Does it visit the secondary loader or not? Okay, that's going to be the interesting planning problem. And our mission, the formal specification here written in English, not in a formal language, is that the robot's goal is to get back to the starting point. Okay, so go around this, get back to the primary loader, and to be empty. So it has to unload, which in this case is the only option it has. So it has to stop at the unloader to unload. It can't go back to the primary load full of ore. And our mission objective, or our objective function that we're trying to optimize in this situation, so something we're trying to maximize or minimize, is the amount of reward we get from a mission. So we can think about the reward we get as the number of banknotes we get. So we might be able to get 10, we might be able to get 6. We could also try and get none if we make some mistake and forget to unload or something. Okay, so this is the general problem setup. And to make it particularly interesting, we're going to introduce a time bound. So this is a very, very rich decision-making problem already. So we have a deadline to get back by. And you can think about this deadline as a configuration parameter on the first loader. We can say that loader is a machine that just every 6 time steps spews out rock in front of it. It's a lot cheaper to build a machine that can do that than one that has to kind of coordinate with some other truck to wait for it to arrive. So this machine is just going to spew out rock every 6 time steps. So that means our truck needs to get round and be back there within at least 6 time steps. So this is a very kind of typical logistics planning problem. And the question we might want to ask ourselves is, well, how much reward can we get from one mission of the robot? And the answer is, if our time bound is 6, then we can get a reward of 10. So if we were doing this in person in a pub somewhere, I would have asked you to work out that and do the maths yourselves. But I'm just, since I think interaction is going to be difficult in this context, I will just give you the answer myself. So we can get 10 reward for executing this policy. So I said policy was the thing we're going to create, and that's what these yellow arrows represent. So the policy of the robot is simply to follow the yellow arrows, and of course unload and load where they're required. So we can get a 10 reward if we've got a time bound of 6, and that's because we're choosing not to collect the secondary load. So if our time bound is 6, we would have an algorithm that would produce this policy, and that would say that algorithm gives you that policy gives you a reward of 10. If we had a time bound of 9, then with this problem, we could always go and get the secondary load. Okay, so if we run at a frequency of 9, or our machine reloads at a frequency of 9, we can always get a secondary load and always get 16 reward, because we can get the primary and secondary load, we can unload them both and get back. So none of this involves uncertainty. So this is where things start to get interesting, is we could introduce some uncertainty. Now, the task of driving around in a mine like the ones we pictured previously is actually fairly uncertain because of the gravel underneath, of traffic. If another truck goes by, you might have to stop. And then this is what we would typically do in that case. We can start to think about when a robot executes an action, we can attach a probability distribution with some properties of that action. Now, in this case, we can say, okay, let's think about the duration of the action. And we can say, with probability 0.2 or 2 times out of 10, the action takes 1 time step. 6 times out of 10, it takes 2 time steps, and 3 times out of 10, it takes, another 2 times out of 10, it takes 3 time steps. So we have this distribution here that's saying we are no longer certain about the way the world behaves when I act in it. And once we start adding uncertainty, the decision about what the robot should do gets a little bit more complicated. So typically, we want to start thinking about the probability of meeting the mission specification. So my group works on algorithms that solve these kinds of problems. And what we can do is we can start to think about the probability of getting back to the start, achieving the goal of emptying the robot and collecting reward with a particular time bound. So this plot shows as the time bound gets longer across the x-axis, on the y-axis we can see the probability of the robot getting back within that time bound. Okay, so we can see here that if we don't collect the secondary load, in our new task, if we've got a time bound of 6, which we started with, now they're only 20% of the time do we get back safely, and we require a time bound of 8 to get back safely 100% of the time. So all of these time bounds make the robot 100% safe, or the problem 100% safe. And I can also plot the policy which gets the secondary load. So this is a different type of robot behavior. It goes the long way, it gets the secondary load, gets more reward. But we can see now that only with a time bound of 11 can the robot complete the task successfully. So then we can start to think about the behavior choices the robot has and how they interact with the time bounds. And interesting, we can ask ourselves, what policy should the robot execute? And we can see that if the time bound's below 8, then, well, there's a chance we might not reach achieve the goal entirely. And if the time bound's 11 or up, then we should definitely execute the policy that visits the secondary loader, because that gives us the most reward. Now, the interesting question we start to have is, what do we do if the time bound is not is somewhere in this region that's highlighted here? If the time bound is 9 or 10, what can our robot do? How can we create a policy that allows it to gather reward? We could just choose the blue one or the green one. But in general, what we do with robots is we build a policy that actually responds to the environment as the robot acts. We actually make policies that allow the robot to make decisions online. And that's what we really want in an autonomous robot situation. We want the policy to respond online. So the optimal policy, which is the best policy, so optimal means best against some metric, actually makes a choice based on time. So say we've got a time bound of 9, the robot can have a policy that says, execute the first action, and then look at your watch, look at the clock, and determine how, count how long it's actually taken to get there. If the duration is only 1 for that previous action, then we can go and get the secondary load. If the duration is longer, then make a different choice and take the shorter route and then unload. And given that policy, we can talk rather about the reward we get in a particular run. We can start to think about the expected reward. So this is what we often think about in robotics. We think about the expected outcome of a particular policy operating in a world or a model. And that expected reward is just the probability of an outcome multiplied by its by the reward it gets, the utility it gets, and we sum this for all the different outcomes. So there's one world in which we can get, I'm not sure these actually match up to the graph. I might need to check that. So in some probability, in some outcome here, 80% of the time we can only execute the policy that gets 10 reward, and 20% of the time we can execute the policy that gets a 16 reward, and we sum these together and we get an expected reward of 11.2. And that's great, because that means it's better than just being conservative and executing. If I jump back, it's better than executing the blue policy all the time, which only ever gets 10 reward. And it's better than executing the green policy. The green policy gets high reward, but in some cases it gets 0 reward. It completely fails and messes up the system. So by having a policy that's adaptive or responsive to the changes in the environment, we're able to actually perform better than in either one of those two cases. Okay, and that's exactly the way we think about planning for autonomous systems. We build these models, we model the uncertainty, and then we optimize the robot's behavior, or plan the robot's behavior to maximize expected reward or some other property that takes into account the probability of the robot having different outcomes when it acts. So we use that in a bunch of different examples. One great example I'll talk about a bit later on is using these models of time to plan how a robot can arrive at a particular location on time. So if we think about robots doing service tasks for humans in, say, office environments, often these are time-bounded, pick up a package, meet a VIP, and some of the work we did worked in these settings where we were modeling the time of the robots working in these environments. And we'll come back to that in a little bit. The other thing we can think of is what happens if the world gets even more unforgiving? So in our previous example, we had an uncertain transition at the start. The robot can make a choice after it. If we have an uncertain choice later on, then the robot can no longer adapt its behavior once it's on this edge, because here it just has to follow a kind of fixed policy. And this means we can no longer, this is where things get particularly interesting, and it's probably true of most robotics problems, we can no longer guarantee that the robot satisfies any mission specification. Okay, because now, in some worlds, we will fail to reach our goal with almost any time bound. So we can think about this in a different way, and there's probably not enough time to go into this in detail, looking at the clock. But we can plot out the probability of the robot getting home safely, the robot getting home empty, against the kind of reward it can gather from a different behavior. And then the dots, the points on this graph, actually respond to different behavior policies the robot can execute. So this is called a Pareto front, and it's a way of representing trade-offs between different objectives. And I think I would argue most interesting robotics problems have multiple objectives. In this case, we have two objectives. One, we want to maximize reward. Two, we want to maximize the probability of getting the robot home safely, of unloading the robot safely. And if we try to maximize one, such as the probability, well, that reduces the reward we get. So if we try and guarantee probability, which means we go to the right here and have a probability of getting home safely of 1, then that gives us the lowest possible reward. And these are kind of interesting configurations of problems that we might need to worry about. And you can think about this as saying, what's my appetite for risk, for example? If I move to the right and choose a policy at the end, I'm very conservative. I want to be safe. And if I choose a policy on the left, then I'm more aggressive. I want to maximize my reward at the cost of unsafe behavior. So these are some of the ways that we're thinking about modeling robot problems in more hazardous or dangerous environments. Okay, and I'm going to jump to that example in a minute. So to kind of close off, that was all very abstract. I want to talk about two specific projects we've been working on and just give you a rough idea how some of those ideas fit in. So this is a project called the Strands Project. It was a European project I ran from 2013 to 2017, so it's a bit old now, but it was very exciting at the time. We put service robots, such as the ones you see here, into a range of care and kind of office environments. And if you want to see me give a slightly more academic talk on this project, then there's a link there on the slides. You're not going to be able to click it, but you can copy it down if you go back and watch this. And these robots were trying to be at particular locations by particular times, so we had to model the uncertainty in the duration of their action in the environment. So a robot's world would look something like this. This is a top-down view of the two-dimensional map the robot operates in. And we divide, exactly as I showed you in that kind of toy example, we divide the world up into these locations the robot can visit. And each of the edges or the lines between these locations represent particular actions the robot can perform, such as going through a doorway or docking onto a charging station to recharge its battery. And we also annotate these locations with things the robot can do, such as looking for objects or learning things about people. Now, there's a huge amount of uncertainty for robots in these environments. The uncertainty comes from the fact that humans can move around, which causes all sorts of problems. Also, the robots can get stuck on features of the environment. They can get stuck on chairs, which is pressing the robot's bumper here. The robot can also fail because humans block its environment. So put up here on the right here, you can see a cleaning brush over the robot's charging station. So this is where the robot needs to dock. And if that's there, the robot can't navigate successfully. And finally, the robot passes through doorways, and we can model the probability distribution of the robot having to wait for a particular duration for the human to open that doorway. So these are examples of uncertainty that robot faces in almost everyday situations. And the way we model that is something called a Markov decision process. If I had a bit longer to talk, I would go through this in some detail. The rough idea, just to give you a high-level overview, is that we formally model the kind of state transitions I've been talking about as actions that transition between states. And we explicitly capture the uncertainty by putting this quantified uncertainty into transitions in this model. And then we can then annotate those transitions with things like costs, which might be time or might be energy usage. And we solve these models to get us a policy. And the robot then executes these as it's driving around. And so that shows you that it's this actual behavior that we've created from models like this, which is driving the robot around. And that typically means it's adapting to the timings in its environment. So in this case, the robot arrives at a doorway roughly when its model predicts there's a high probability of a human opening it. And in this case, the robot, this is shot from a kind of robot's eye view. And again, we've got the robot is choosing, in this case, to navigate through the doorways at times when humans are more likely to be around to open the doorways. So it's modeling the uncertainty. It's using that uncertainty to tell it when it should act in the world to maximize the probability of successfully navigating through this setting. And this is an example where the robot had to be somewhere on time to help some nurses walk some patients around in a care home as well. But I don't really have time for this example just yet. So I want to give you one other example from a slightly different context, something reasonably close to home. We're working in a lot of nuclear inspection tasks where robots are inspecting nuclear facilities in areas that are very hazardous to humans. The pictures here are from a trial we ran last week where we had a heavily customized robot operating, in this case, it's kind of remote controlled, inspecting the hall around the jet fusion reactor in Cullen. And these kind of ideas where robots have to work in hazardous environments is something we've been thinking about a lot. So we have actually a slightly different problem. So this is a different setup. And here we're kind of faking the radiation. But we've got this general idea of an inspection robot that must visit multiple targets to gather information without it exceeding a radiation dose, because high radiation doses over time could degrade the components within a robot. And we can model the environment a bit like this. So we're going to show you a similar map. So this is another top-down view. And these colored discs represent the targets a robot should go and inspect. So this is a robot driving up to a location, gathering some information on gamma activity, for example. But we've also got some radiation sources. And this is a nice example of a multi-objective problem again. Okay, we want the robot to go to these colorful locations to get some information. But to go to these colorful locations, it has to experience some hazard. It has to go near these radiation sources. And so we think about these in exactly the same way as this kind of multi-objective problem. We want to trade off the probability of successfully completing the mission, which we can see in this blue bar chart. And that means getting back to the start without exceeding a particular given dose of radiation. And then we can also think about the reward. So how many locations does the robot visit? And a reward, in this case, a normalized reward of 1 means the robot can visit all those locations. And so we solve similar problems using the same techniques. We model each action not only as having a duration, but also having an expected dose of radiation. And then what we do is we can come up with one of these Pareto fronts again, and we can choose policies from this front. On the left, we're more aggressive, so where my mouse is here. These are policies that visit more locations. And on the right, we're more conservative. So the robot experiences less radiation, but to get less radiation, it's also getting less reward. And we typically, it's a long conversation, but we typically choose something like this, where the robot is getting less reward, but still quite high probability. And I'm just going to let one of these, I'm not going to let this one show, I'm going to just run forward. This is an aggressive policy that the robot's running. This is a top-down view of one of the examples where we saw the robot driving around in the environment previously. This is sped up 20 times, so the robot's zooming around. This is filmed up in Moreton in Marsh, where there's a fire service training college. And so this is actually in a mock oil rig, so not in a real radiation example. But you can see here we've got some probabilities. In this case, even though it's aggressive, there's still a very high probability of success. So in fact, when my mouse is here, we're just under 1, but that's great. And you can see here we're tracking a kind of simulated radiation dose. If that radiation dose suddenly jumped up high or dropped down low, then the robot would respond by changing its policy. In fact, you can see some of these arrows change slightly as the robot's moving. That's adapting the policy to the observed radiation doses. But it's not super visible on here. Okay, so that was a massively quick dash through the topics that are super close to my heart, which is allowing autonomous robots to operate safely and successfully in the environment, performing tasks for humans. And they do that by quantifying the uncertainty present in that environment. That uncertainty might be a delay in navigation due to it having to take a long time to navigate around humans. Or it could be, the uncertainty could be due to the dose of radiation it accumulates through a kind of a real stochastic process. We build models of the way the robots interact with the world. We build models of the systems that say, this is how we expect the world to change. And we factor in that uncertainty. And a whole space of things that I haven't talked about are how we then specify the problem we want the robot to solve, such as maximizing the reward or trading off some information gathering against safety. And then most of the work I do, most of the work my group works on, is actually writing algorithms that produce these kinds of policies such that the robot displays smart, intelligent behavior in pursuit of that specification. So most of the actual work we do is not about modeling the probability, but it's about producing algorithms that solve these problems in order to control the robots at runtime. And that's where the bulk of actually the interesting work is. But I think in terms of understanding what autonomous robots are doing, what autonomous cars are doing when you see them moving around, is actually performing lookups in these kinds of policies to maximize some kind of reward as they move around the world. Okay, so that is me more or less done. Thank you very much for listening. I assume someone out there is listening. And sorry for rushing through it quickly, but I think it's better almost to get to the end and then sort of take questions, and I can go back through some of it in a more directed way. So thank you very much.
Thank you very much, Nick. I definitely was listening, and we've still got people on the YouTube channel, so there are people out there that have been listening. And yeah, really interesting. I'm sure you probably could have spoken for a couple of hours on at least.
Yeah, oh, for sure.
Really, really fascinating. So yeah, if anyone's got any questions, please pop them in on the YouTube video. Jutta has already posted a question. She posted it while you were still talking, so I can bring hers up now. So Jutta says she's read several times about cleaning robots doing their job unsupervised, and more than once animal poo has been spread around that was supposed to be clean. So how would you avoid this?
Cool. Hi, Jutta. So I mean, there's many answers to that. So that's typically a perception problem. So the robot needs to have sensors that allow it to detect there is something on the floor that it shouldn't be driving into. But what's particularly interesting, so I'll answer this from a different perspective, which is I talked about a robot having a model of the world. And so when you develop or design an autonomous system, if you want it to be able to use sensors to perceive something and then respond to that thing, you have to include the description of the thing you want it to know about in its model. So in this case, you have to include the dog poo or the cat poo in the internal model, in the software of that cleaning robot. And that kind of sounds fairly sensible, but then you start raising the question, where do you stop? Does it need to know about Lego and cats and children's toys and all these other things? And so typically designers of autonomous systems will draw a line somewhere. It seems in this case, maybe poo was, it drew it on the wrong side of the line, drew the line on the wrong side of that. But this problem of modeling the world for an autonomous system is this massively open-ended challenge. Yeah. And the more complicated your model, the harder it is to produce a behavior policy in any finite amount of time. So there's this trade-off between modeling complexity, behavior production, and also the sensors you need. I mean, you need sensors then to detect animal poo. You need a sensor to detect Lego, people's feet, etc., etc. Yeah. So, yeah.
Thank you very much. So we have a question from Neil, who asks, how far away are we from robots being able to create new versions of robots to overcome deficiencies or limitations?
There's a very trivial answer to that, and a longer answer to that. So the trivial answer is we have it now, in that even the robots that I talked about in that video, every time they run, they're gathering statistics. So I talked about quantifying uncertainty. We actually get those measures of uncertainty, those models of the way the world behaves, by gathering data as the robot acts. And so they are creating, and then effectively what happens is they go to sleep, they run some statistical processing and build new models for the next day. And so they are creating new versions of themselves that act the next day with a little bit more information about the world behaves, the way the world behaves, and they'll be a little bit more reliable or a little bit more robust. So absolutely on a kind of incremental, I mean, it feels like trivial, but it's quite a powerful way of thinking about it. These robots are gathering statistics about their own behavior and improving themselves day by day. And there's lots of different versions of kind of AI methods that do that, different types of machine learning methods that do that. In terms of maybe the way your question was kind of angled around the kind of more sci-fi, you know, a robot detects a limitation that it can't solve a particular problem, so it reprograms itself, or builds a new limb or something. That has this massive problem that Donald Rumsfeld made kind of popular, about like knowing the unknowable, right? So for a robot to be able to maybe detect that it has failed is fairly achievable. Being able to understand the reasons by which it failed is a completely currently unsolvable question. Yeah. So you can take it back to the problem of the animal poo, right? The robot is day after day is happily cleaning the floor. Then one day it gets switched off and told you're never cleaning the floor again, because it's smeared poo everywhere. How is it, what does it need to have in its software to understand it has made a mistake? Yeah. And then to have a robot that could understand every possible cause of every mistake in the world is beyond the, I'd say it's not even a well-founded problem in computer science to even formulate that. We don't know how to do that. Yeah. And so that kind of that's typically called, there's a set of problems that are called big AI or strong AI, which typically means that if you can't solve any of those problems without creating kind of human level intelligence. And we're a very long way away from that.
Okay, thank you very much. So we have a question from Bob, who asks, are they using these AI solutions on the Mars rovers and the little helicopter that they've just tested on Mars?
Yeah, to some extent. So I don't know for sure what they're running on the helicopter. That'd be really interesting. So actually, someone I worked on one of those robotics projects worked on the helicopter, so I've got a slight connection to naval hypothesis, which is exciting. The Mars rover itself is absolutely modeling, is planning its behavior and executing its behavior in that kind of model. I'm not entirely sure it models the uncertainty that explicitly, and it doesn't, at least. So I'm not sure about the current Mars rover. So so Spirit and Opportunity, the way they worked is they would come up, effectively ground-based software would come up with a mission plan for the day. So there would be a model of the robot's capabilities and a rough model of the Martian landscape and things like that. And some AI software on planet side, on Earth, would come up with a plan, which would be, here are the actions the robot's going to perform. And then it's basically put in front every day. It's put in front of a room full of scientists who are both kind of robotic scientists, understand whether that's safe for the robot, and NASA, planetary scientists, biologists, whatever, and they decide if the robots if that algorithm has made the right choices in terms of the scientific work, and then the humans tweak the plan, right? And then it gets uploaded to Mars. Yeah. So absolutely, this kind of general approach of modeling the environment, coming up with plans, and then executing them is being performed on those kind of on the ground rovers. I suspect the aerial rovers are following a much simpler pattern. So if you've got a reasonably straightforward system, you can effectively just write a fixed plan that works forever, which might be just fly up, fly left, land, take a sample, come back.
Yeah.
And you don't need to know about your environment too much. And then they'll have some controllers that stabilize them and things like that. So I would say that certainly the ground rover which has got to deal with long-term autonomy, has to do like long transits across Mars, will be using a model of its behavior and its objectives, but with a human in the loop deciding whether that's actually safe and the right thing to do, because these things are super expensive. You don't want to mess up. And then the little helicopter, what's the helicopter called? It's got a cool name. Sorry, I put you on the spot. Is it Perseverance or is that the Rover?
Perseverance is the Rover. I'm sure one of our audience members can remember what the.
Someone can Google it while we're talking. Anyway, I suspect that the helicopter's using a much simpler behavior structure.
Okay. Thank you very much. Oh yes, Ingenuity. You have to confirm. Okay, thank you very much. We've got another question here from Andy, sort of links back into what you were discussing previously. So with the seemingly limitless applications of AI, do you have any genuine concerns about nefarious use of it or the possibility of AI robots becoming sentient in the future?
So I mean, I have genuine concerns about nefarious uses of AI because it's happened already, right? There's lots of evidence of maybe not nefarious, but damaging uses of AI. So people have been using kind of machine learning systems that are racially biased. Mm-hmm. There are sentencing systems that are biased by the data you give them. So these are systems that are not nefarious in themselves, but they're being used by humans that do not understand their strengths and limitations, and therefore they're being used inappropriately. And there's arguments that nation states are deploying AI to do large-scale surveillance of minority populations and things. So I have genuine concerns about nefarious use of AI because it is happening and it should be legislated against. Whether that's AI or whether that's just technology in general, I think is an open question. AI is part of that suite of things around big data and connectivity that's enabling some nefarious behavior. Possibility of AI robots becoming sentient in the future, much less worried about that. I think that's a red herring. It's just there's no, as someone that spent my life programming dumb machines, I just don't see that. I don't imagine a world in which you suddenly write one more line of code and the system changes from being kind of this dumb input output thing to something that is more than the sum of its parts in some way. I also take humans as an existence proof that an engineered system can be sentient. So, it has to be possible, but this version of at some point machines just sit there for long enough and then become sentient, I'm not sure. And I'm not sure how we get there by engineering either. So
I guess maybe we'd need a more thorough understanding of our own intelligence before we can start implanting it upon other things.
I would say we need both that and a more formal definition of what we consider sentient. So I think like for things like consciousness, we don't necessarily have a good definition that we could reproduce in a machine and be satisfied with. And people are actively working on that, and there is progress in that direction. But even to make it a testable scientific question is still open, I think.
Cool. Thank you very much. I think that's it for the questions. We just have a comment from Liz who says, thank you very much for a clear exposition. I'm a non-scientist, so missed some finer details, but found the gist of what you've explained fascinating and comprehensible.
Thank you very much, Liz.
A very nice way to end the session. So yeah, thank you again, Nick. Really appreciate you spending your time with us this evening. And it really was a very interesting talk. Thank you everyone who came along and watched. The video will be saved on the YouTube channel as per usual. So if you know anyone who might be interested, please do let them know. They can come along and have a look. And we will see you all soon.
Cool.
Bye.
Bye. Thanks.